All right, hi. I'm going to talk to you about something that I've been working on now for about 10 years, and it's the idea of following up on a little bit on what Larry was just saying, which is producing houses. All of his work is about specifically producing a certain type of house, and what I've been thinking about for the last actually 10, maybe 15 years is using the computer to produce houses, especially today in the information age. But I can't talk about my interest in housing today without talking about my grandfather. My grandfather was a man in Virginia. He only had a sixth grade education, and he built this house for his six children and my grandmother with just a few very simple tools, very common tools, saws, uh, drills, knives, blades for cutting tiles and things like that. But he did a great job with very little. In fact, I definitely I couldn't do that. I can't even build my daughter a playhouse. So just the thought of being able to do something like this has always intrigued me. But I grew up in New York City, and I watched this architect, Max Bond, since I was in high school, build low-income housing for people in my neighborhood, which was Harlem. And I noticed that he had a really great way of getting good, high-quality housing to large numbers of people at a somewhat reasonable price. But I don't think that's always possible today, and I'll sort of explain why. I think most of us always ask the question, why is construction so complex? Why is it that when a tsunami hits, or an earthquake, or a hurricane, why is it that it takes so long to rebuild all of these rich, interesting houses that we've lost? A great example is New Orleans, which is still struggling. Well, it's very simple. The one thing that all carpenters do and designers do is compute. It's a common theme. Everybody computes, which means that everybody's counting and thinking about geometry and how objects fit together and how to count steps in producing an object. So here, for example, you have a designer at the left-hand side, a contractor interprets the drawings, someone takes that interpretation and marks it or measures it out onto a piece of material, cuts and assembles that. One problem today is that the person at the end of the chain has very little relationship with the person at the front of the chain. The designer has no influence on how things are assembled in construction, and the people who are all the way at the end of the chain can never participate in the design. So if you look at the colored image, for example, of the house, it's a James Cutler house from the 1990s. It's a wooden structure, wood framing, which is the yellow, which goes up very quickly. Wood framing always goes up very fast. And the complexity is getting all of the other colors onto it, the slabs or the tiles, roof tiles, waterproofing, getting all the additional materials, flooring, getting all of that stuff cut, measured, and assembled. So the complexity is in the red, the blue, and the green person. Each component in the house has to be touched, measured, and manufactured by someone. So if you have 10,000 pieces, you have 10,000, you're repeating that step 10,000 times over. Pre-manufactured housing is no different. You're paying for all of those steps, plus you're also paying for the heating of the factory, you're paying for the crane, you're paying for the truck. You're also paying for a double the structure. You have to structure the box for movement, and then you also have to you add more structure to the box just to make it a little bit stronger, but you're paying for a lot more. So the industrial process is a very labor-intensive, and in many ways, I think, out of control method of production. So today in the information age, we have a way of producing things that we're probably not even thinking about or aware of that's happening around us, which is the idea of decentralized production. And if you think of decentralized, you could probably think of like what's been going on in the Middle East. There's no single person that's in control of all of the things that have been changing, but you could tell that there's some level of control. So the question is, how can we do that today? And here's a sketch that explains a little bit of what I'm talking about. So you have to imagine the digital designer, the person sitting at the laptop, downloading a file or downloading a series of files, and then they send that to a machine that's run by the computer. And the machine doesn't just cut out parts, raw parts. The machine also puts a number on each part, and the machine draws each part or cuts out each part so that it only fits in a certain location in a certain way. And back in 2005, I had come up with this idea back around 2003, but in 2005 I had a chance to build a small cabin which was made out of all interlocking parts. It was about 80 square feet, all interlocking plywood pieces, no glue, no nails, screws, anything. And again, it's because you can calculate how things go together, and you could also calculate the strength of each part. So this image shows a little bit of the advantages. The first is that everyone can participate in the process. So I have two students here, Dan Smithwick and Dennis Michaud, and what they're doing is they're building the computer model. They built the two computer models up at the top. One is the skin, and one is this internal lattice. And they built them separately on two separate computers. And then they brought them together by prototyping the pieces. So they ran the pieces through the laser cutter. The laser cutter cut out all the parts with all of the connection pieces, and they were all numbered. It was all encoded on that one piece, or each piece, and then they attached them together to check and see if all the pieces fit. And I'll show this project a little bit later. It's a museum exhibit in New York City, and there's Dennis up on a ladder assembling the parts that he just laser cut about a month earlier. But the process, I was inspired to do this by looking at three-dimensional printing. I was introduced to three-dimensional printing by my PhD advisor, Bill Mitchell, and in the late 90s. And the one thing that happens with three-dimensional printing is it automates the three areas of computation that I just mentioned. It takes in a three-dimensional model from a designer, a kid, anybody can print with a 3D printer, takes in a model in 3D. It scans a section through the model, does a calculation where it creates the contours around a section through the model, and then it prints one layer at a time, just like a layer cake. And each layer is adhered to the previous layer. So as an automated system, it's doing three things at one time. It's measuring, manufacturing a layer, and then it's assembling that layer to the previously manufactured layer. So it's doing those same three operations in one shot. And you can produce really beautiful models like the one in the middle. It's a model of a New Orleans shotgun house. But then at the bottom, a really good friend of mine, Barak Kajnevis, back in 2002, came up with the idea of house printing and printing with concrete, as opposed to printing with plaster or plastic. And his idea was that you would print in big, nice, thick 3-inch layers or 2-inch layers of concrete, one layer at a time. But you can imagine that gets a little difficult and redundant, and it's not scalable. If you need a house, you need a machine the size of a tall building. If you need a tall building, you need a machine the size of a gigantic building. So it makes it very difficult to scale that type of process. So my idea was almost the same thing. Take a three-dimensional model, read in that data, run calculations over that model, and then develop the pieces into two-dimensional sections and cut them with a laser cutter, or a CNC machine, or a water jet cutter, or some cutting device that's controlled by a computer. So here what I'm showing is a ball that was first made in the computer, and then we ran it through a few computations, and it managed to develop all the little parts. But then we were also able to take each section and turn it into a variable, and then again calculate attachment features with each part. So each part has an attachment feature, an association with the next part. So looking at this a little bit larger, I realize this drawing is a little hard to see, but I'll explain it. You're looking at a small cabin, about 15 feet by 30 feet. And what I've done is the same thing. We take in a three-dimensional model, we take variables from that, we calculate, we store those variables, and then we do calculations on them. So the one in the middle, the image, the little square in the middle, or the box in the middle, shows finite element analysis, calculating that building using a computer program to test it for structural capacity. And then if it passes, we then go through the same sectioning process that I had mentioned with three-dimensional printing. We slice the model in sections, but this time we do it in 3 dimensions. Instead of just slicing in the Z direction, the way that we did with the layer cake, this time we slice in X, Y, and Z. And then we end up with contours. So if we look at a contour a little bit more closely, you could see from looking at the size of the person that that contour also needs to be subdivided into small parts. It needs to, again, go through another computation. And carpenters do this. This is exactly what carpenters do. They take parts, they figure out what the maximum size of the part is, they divide that part up by a certain number, they calculate on a piece of paper what it should be, and then they recut the part that they just cut. So then here are a couple of other calculations just looking at the surfaces, but this is another operation called development, where you take a three-dimensional shape and you convert it or copy it to 2 dimensions, pack all the parts together, sort them, and then fit them all onto a sheet and give each component a number. So if we look at this slide of a part being cut, the part has a number of small, little, tiny micro fabrication pieces to it, cuts to it, and it also has a number. So to give you an example of how this works, I showed you the cabin. Here's another project that I worked on back in 2008. It was a commission from the Museum of Modern Art. They had a show called Home Delivery, a 4-month-long exhibit. On the inside of the museum, they had models and drawings that showed houses from the past, like the Lustron house or the Package house, or some of the other really great inventions of their time. And on the outside of the museum, they had full-scale buildings, 5 of them. One was a tower that was made out of aluminum, 2 other ones that were small buildings, really meant for 1 person, and the 3 in the back, mine on the left, the shotgun house, the one in the middle, the long bar, and the yellow one in the back, the burst house. They were all cut by digital fabrication equipment. They were all made pretty much the same way, but they're different buildings in different shapes. So we cut all of our parts from that 3-dimensional model that I showed you that Dan and Dennis were using. We cut all of our parts in Exmoor, Virginia. We then mailed all of those parts to New York City on the back of a truck. It was 10 packages of 45 sheets of plywood, but they were all had the shapes cut out of them. When we opened each, or finished with each sheet, we'd cut out the next set of parts. And this took some real careful calculating. You had to make sure to it that the sheets at the top of the package were for the bottom of the building, and the sheets at the end of the package were for the top of the building. So you couldn't just randomly pack parts onto sheets. You had to really think very carefully. And then we hammered all the parts together using just a mallet. So for 4 months, that structure stood, and we didn't use glue or nails to hold any of the parts together. And there were 5,000 parts in the entire structure. And what was best was it was rated for 75 miles an hour. We had to get a real structural engineer to calculate whether the building would stand up under wind loads, and he certified it for 75 miles an hour. But his computer model showed that we could easily pass 140 miles an hour. And it's because we had solid corners. So here's just looking at the details. The details came in after we finished prototyping the structure. What was really nice is here's Laura Rushfeld. She came in sort of after Dan and Dennis had finished. She just recut some of the structural skin, that last layer, herself, and when she added a new ornament, she would go back and take that piece out of the computer model and then recut that one piece so that the ornament would snap on. And we cut all the ornament at MIT. We didn't cut this in Virginia. And what was really beautiful was that the ornamentation, once we started applying the ornamentation to the structure, it all fit perfectly. So here was a person who had no connection to the first 2 people, and she was able to design and work with me very carefully on designing all of the little tiny parts, like the rails, the coins on the side, which are square pieces, doors, windows. If you look, they're perfectly straight. Really nice, smooth, high-quality construction. And here's just a shot showing 2 other students assembling the parts. A novice can assemble really intricate woodworking and wood parts. And what was really fantastic, this is the best part about this image, there was the woman in the lower right. She works for the museum, and she had passed by us watching us put this building together over the course of 22 days. And she said, "You guys look like you're having a lot of fun." And so she took a day off of work, and we just gave her a hammer, and she just started hammering parts on. And she was hammering on the details, the stuff that's very complicated and hard to make. So this is the finished building. It had We had a number of visitors. We had about 1 million visitors. We took the prototype model that we built at MIT and we put it in the middle of the room. And the prototypical model is exactly 1/6 the size of the real one. So if we know if the prototype works, the real one works. So what I've been thinking about since that exhibit has been the idea of integrating other systems into the building. What I just showed you was just the structure. It wasn't the plumbing, it didn't have bathrooms, it didn't have kitchens. So my question now is, can we integrate all of that stuff into the building? Can we make the building function a lot like a nice car, right? Get in your car, take your phone, you can make phone calls without, well, most of us can make phone calls without, tapping in our numbers. We can use the steering wheel. So the idea is integrating systems into wall structures. So this is a printed circuit board, and of course printed circuitry was developed back in the 60s with the same concept as digital fabrication. You take a computer model and you send it to a machine and it prints out metal onto a fiberglass board. And then here, this is water jet cut aluminum. And the question is, can we make aluminum shapes and cut out aluminum parts so that they fit together and work much like the stuff I just showed you, much like an integrated part that was the trim that was integrated into the structure. Could we do the same thing with a wall system so we have plumbing, electrical, insulation, et cetera? So now we're practicing this on the idea of replacing trailers. Trailers are all over the States and also in other countries as well. And the idea would be to take the configuration of a trailer, let's say one like the lower right, which is the closest to the configuration of a trailer where you have living room, dining room, kitchen cabinetry. And can you take that same configuration and change it around numerous times, make a round shape like a yurt, and then fit all of that into a trailer, but change the style. Create buildings that are the styles that people want, whether they're modern, arts and crafts, shotgun, doesn't matter. Every person has their own style that they like, and the key is marrying the function to the style, the personal style. So can you use computers, given all the flexibility that they have, working with other people to accomplish this? So just to conclude and summarize what we just went over, make the point very clear. Digital fabrication has to be the next step in home production, especially for small home production. There's no reason why we can't build small homes using computers using machines that are attached to computers. It's the way IKEA works. It's the way that all kitchen cabinetry is manufactured. So digital fabrication is the first step. The second step is getting other people to participate in the process. So I showed you how 3 students worked on this process. There were also a number of other students that had worked on this. There were about 12 students in a course that I had taught that same semester that also participated on the design of all the components that I just showed you. We could do this on a global scale as well. And last is thinking very carefully about smart surfaces, how we can work on integrating a lot of functionality into surfaces so that buildings perform a lot more like a luxury car or a wonderful piece of electronics that we just bought. Thank you.